Before starting my talk, I would like to forward a few words. I do not agree to the statement made by Lev Weidman this morning. In my talk, I will show that by using age-invariant dynamical variables, it is in fact possible to determine where the AB effect occurs. This is not a matter of interpretation. By this I mean that one has to consider not only the relative phase, but also the vector potential. And the details you will see here in the talk. I will also show that this statement can be verified experimentally. I will start now with, go ahead with my talk. The subject is a non-local dynamical exchange that is responsible for the shift of the interference pattern. It is based on an article by Aharonov and myself and new results. I will first talk about modular momentum, and then I shall discuss exchange of modular momentum with the AB effect. I'll speak now about modular momentum. Consider a particle in superposition of two wave packets with a relative phase alpha and separated by a distance L. We are focusing on modular momentum since this is a dynamical variable that is relevant to quantum interference. Modular momentum is represented by the displacement operator e to the IPL, whose average depends on the relative phase alpha. Since the displacement operator maps psi1 onto psi2. By comparison, averages of polynomials in X and P do not depend on the relative phase. Modular momentum has two important attributes. The first is that it has a non-local equation of motion. As you see here, the change in modular momentum depends on this non-local potential difference. The periodic step potential with step widths of L induces this change in the momentum modulo L. This particle that sits here experiences non-local and forceless interaction. And if the particle is in a superposition of two such wave packets with a separation of L, then it acquires a relative phase under a non-local and forceless interaction. Modular momentum is also a conserved quantity. I now relate to a collision between two particles. Pi1 and Pi2 are their respective modular momenta. And in the collision, the modular momentum is exchanged on an ellipse. And the system shifts from point A to point B, for example. Finally, I would like to mention that modular momentum is the only way to describe interference in the Heisenberg picture. The reason is that in the Heisenberg picture, the state is fixed to be the initial state. So there's no way to account for changes in the relative phase, unless, of course, one uses modular momentum. Yakir says that Heisenberg himself was aware of this seeming shortcoming of his picture relative to the Schrödinger picture. I will now relate to the AB effect. And in particular, I will show that an abrupt change occurs in the gauge-invariant modular momentum e to the I mvl of the external particle when the line connecting these two wave packets crosses a solenoid. I will next show that this change in the modular momentum is responsible for the shift of the interference pattern of the AB effect. And finally, I shall describe a Gedanken experiment that shows that this prediction is verifiable experimentally. The abrupt change of modular momentum follows immediately in the singular Cherenkov gauge. Here, the vector potential is non-vanishing only on the positive y-axis, and it is proportional to the total flux. If initially the external particle is prepared in a superposition of these two wave packets, and just by crossing the potential line, it acquires a relative phase that is equal to the full AB phase. Not also that the gauge invariant momentum, that both before crossing the potential line and also afterwards, the gauge invariant momentum equals to the canonical momentum. And therefore, in order to calculate the change in the gauge invariant modular momentum, one need only consider the usual modular momentum, and one obtains this alpha-dependent result. The change in the gauge invariant modular momentum occurs via non-local interaction with the flux line, from which the external particle has been excluded. And before I described to you a scalar potential analog of such an interaction, of such a non-local and forceless interaction, which also led to change in the relative phase. Finally, the velocity distribution also of the external particle also changes when it passes by the solenoid. And the reason is that the average modular momentum is really the Fourier transform of the velocity distribution. And in other gauges, one may have to use this general formula. I will now consider that part of the evolution when the two particles are brought together to interfere. In the gauge that we are considering, we have now a free Hamiltonian. And the time t equals 0 is defined as a time when the two wave packets start to move towards each other. And as you see, this occurs after the particle has already passed by the solenoid. And this means that the modular momentum has already changed by this at t equals 0. Capital T is the time when the two wave packets meet. This picture is also, the interference pattern is also thanks to Professor Futonomura. And L of T is their instantaneous separation. I will now switch to the Heisenberg picture. And in particular, I'll consider the motion in the y direction only. The Heisenberg state is described here, and as you see, I've assumed that it has already a relative phase e to the minus I alpha. The relevant function of modular momentum is a of 0, which is a constant of the motion, since both the momentum and y of 0 are constants. And its time evolution is given here by a of t, which, as you see, is proportional to the instantaneous modular momentum cosine py times L of t. By the time capital T, A has transformed into this local function cosine 2k naught times the y of capital T, which describes interference in the Heisenberg picture. Now the average of A of 0 equals to cosine alpha, and A is a conserved quantity. Therefore, A of 0 equals to A of t. And it follows that the average of A of cosine 2k naught y of capital T also equals to cosine alpha, which means that the shift of the interference pattern. We have the scene that the change in modular momentum which occurred when the particle passed by the solenoid and the two wave packets were still apart manifests itself later on as a shift of the interference pattern of the AB effect. And here I will relate only very briefly to the change of angular modular momentum. This is described in the reference frame where the particle is at rest and the solenoid is moving. Note the change in the angular modular momentum when the solenoid enters the circle and again as it leaves it. And now this is a Gedanken experiment. Initially, the charged particle, which is the ball, is in this state, in this wave packet psi of y, and an external uncharged particle is approaching, and it is in a superposition of these two incoming wave packets. Don't notice these mistaken signs. when the external particle hits the ball, the latter moves for a distance L and comes to rest. But the external particle hits the ball at an uncertain time, and therefore there is an intermediate time interval when the ball is in two wave packets, psi y and psi y minus L, and the two particles are then entangled. Now the charged particle ends up in this wave packet psi y minus L, and the external particle has been reflected and moved downwards. And this is now a superposition of these two downgoing wave packets. And notice also that it's in the final state, the relative phase due to the solenoid that has been transferred to the external particle. And this can be measured in an interference experiment on the external particle. Now, let us consider the time evolution of the charged particle. This is a central point. The time evolution of the charged particle is described in the plane y, in the yt plane, specifically the plane x equals 0, since that is where the charged particle is positioned. Now the solenoid, in its motion along the x direction, crosses this plane at y equals 0 and at a definite time. Oops. Mousing. How do I... איך אני חוזרת לסוף? Okay. As I said, the solenoid in its motion along the x direction crosses this plane at y equals 0 and at a definite time, say the time t equals 0. Now the solenoid, because of its motion in the x direction, has also an electric field in the y direction. Oops. אבל תחזיר את זה למצגת, איפה זה? אופס.
מה את רוצה רק לדף האחרון?
טוב, נעזוב את זה, אני לא אגע בזה יותר. הנה זה. אוקיי, ותשים את זה למצגת.
זהו, אבל זה השלייד האחרון.
כן. So the solenoid, because of its motion in the x direction, has an electric field in the y direction. So that when it crosses this yt plane, there appears at the origin an electric flux that equals to phi, the original flux of the solenoid. And we have thus here an electric AB effect, and the charged particle acquires a relative phase. And as this occurs, it's a plane x equals 0. And as I showed before, this is the way this change in the relative phase can be measured on is observable as a shift of the interference pattern of the external particle. So, and if this shift of in the interference pattern of the external particle is observed, it cannot have but occurred at a definite x. And thus this shows that the change in modular momentum has occurred at a definite x, exactly that is when the solenoid passed between the two wave packets of the charged particle. Okay, thank you. סליחה?
תחזרי על השאלה לפני שתתני את התשובה.
First, I'm pleased that there are disagreement. I think if everybody agrees with everybody, we cannot go forward. Second, I'm not absolutely sure that there is a disagreement. Because if I understand, you define this non-local variable, and you say with this non-local variable we have a change in particular moment.
Is a particular position, is in a particular geometry, sorry, there's a particular geometry, not a particular moment.
Yes. I understood that your method of measurement is that you said you have to interfere your testing particles. But the whole idea to measure
what do you mean?
You have to do local measurement. If you bring them together, of course there is.
No,
you said that how you know that where it happened, because there is interference of your test particle change. You have to bring it together, so it's much later. The question: can you measure it locally? If you cannot measure it locally, you really cannot know when it happened.
Okay, you see the measurement on the external particle is a priori, is a posteriori, is later, occurs later, but it cannot have, but the shift of the interference pattern cannot have occurred, but this electric AB effect is confined to the x equals, to this definite x equals 0 plane. So it cannot have occurred, but in this plane, the electric AB effect is confined to this plane. So it cannot have happened otherwise at another place. Okay?
May I say something? We can speak about the probability distribution of velocity and speak exactly the time when that is changed.
You can come the mic. Go to the microphone. The other one. This microphone. Then it will be recorded. And you go near Ronnie. This is fine and ground. This is good enough.
There is a gauge invariant quantity, which is the velocity, which is equal to the momentum minus E over C times A. And we can speak about the probability distribution of that velocity. That probability distribution has Fourier transform, so if the Fourier transform has changed, it means that the probability distribution itself has changed. And we can ask the question, at what time did this probability distribution change? And it's in exactly that time that when the two wave packets are crossing, as shown in this picture. So we can speak about an exact time when the probability distribution of the velocity has changed, and it doesn't matter how long we have to wait later to see that change. The question is that the equation of motion tells us exactly at what time that probability distribution of a gauge invariant quantity has changed. And that, therefore, it doesn't depend. If we look only on the wave function itself, or in its phase, that's not a gauge invariant quantity. Then we get confused when this phase has changed. But when we speak about gauge invariant quantities, like the distribution of the velocity, then if the equation of motion tells us that has changed at a given time, that's it, that's the end of it. And there is no confusion anymore. So by looking at the wave function, we get confused because that is a phase. The phase is not a gauge invariant, so we don't know when this phase has changed. But when we look at the gauge invariant quantities, which are the velocities, and we look at the probability of that, and we ask at what time that has changed, it has changed exactly at that instant where the line connecting the two wave packets has crossed the solenoid.
If you want to be heard.
Yeah. If we consider non-local variables like velocity, then you're absolutely right. But if we're in a position that we think that everything is a wave function, and what it is an wave function, and the property is this relative phase of a wave function, then this relative phase of ovation, we don't know where it's happening. It's just because we use this non-local properties, we can use this language. I still believe that the physics is local, and the Aharonov-Bohm effect kind of has this paradoxical property that it has the non-locality. I believe that in this way it's less paradoxical. If we use local description of the wave function, we cannot know when the relative phase was gained. It's
But
just because...
It's not a gauge invariant quantity, so can you ask when it has changed? There are gauge invariant quantities which are the velocity and when, and their change happen exactly, and they are responsible later for the change.
But there are non-local properties that I don't think that this is a... Okay, there is a possibility to describe physics in non... I believe that the physics interactions are local. So non-local properties are not a good way to describe them. If you define these non-local properties, then you can make all kinds of things what happened with them.
May I say something? If you exclude velocity from physics, so what remains?
It's not that I exclude. I think this is also fruitful, but in this way we cannot say when you look. Yeah.
I take Yakir's point about velocity being a gauge invariant quantity that one should study, but I'm surprised that you speak about the instant, because it isn't an instant. The wave packets have an extension in space, and it takes some time.
I know, but that is much less than the time it takes to bring them together. There are two scales of time. The time when the width goes through and the time when you bring them together. That are completely different scales. Yeah.
But one more point. I mean, in the usual ways of speaking about AV effect, one thinks about either an extended beam or even a plane wave. Now, there one has an interference pattern, but one doesn't have wave packets. So I suppose the interpretation makes sense, of course. You probably agree that the way in which one interprets the formation of the interference pattern depends on which configuration of the incident particles you're thinking of in the experiment. Right. And you're now thinking, as she taught in the lecture, of having wave packets. With a plane wave, it would appear different.
Oh. Okay. Anybody else? Okay, thank you.